All right, let's get started. Good afternoon. So, do you have any questions about what we covered so far? So in general, so far we've been kind of like going at a very high level. We're introducing lots of terms which may or may not be familiar to you in terms of audio, video, and images and stuff. And we'll use many of the stuff as we go more deeper into some of the compression and stuff, right? So far we looked at audio, images, and video. The takeaway message here is audio tends to be a two-dimensional structure, like so there's some value which changes with time. And images is a 2D matrix, and the corresponding for audio is the video, where you have a matrix every so often, right? So where you had for audio, all you had was at each time instant you had some constant value. Now you have a 2D matrix. And there are lots of different ways of saying this, but in general, higher fidelity, meaning like if you have more data, you tend to have better stuff, right? So if you have more quantization, maybe you get better sounding audio. If you have more bits per pixel, then you get better colors, more variation, and what have you. And the key is, if you deal with this as data, then essentially your audio stream would sound like a string of integers, and video would sound like a string of matrices, which you can make them into a string of numbers. And if you treat it as such, the amount of data which is created is very high. And so our goal is to make sure that we can manage it somehow. And the compression is essentially our first step in managing this. The better the compression is, the fewer data we have to send, and that will make all our future stuff that we will look into simpler, right? And the goal here is to make sure that we use as much of the knowledge from physiology and all those things are possible. Example, the Weber's law and all those things, to see what we can lose and still get a good quality, right? So at the end of the day, after we do all this stuff, you won't be able to tell the difference between the original and what you've seen, and that is important for a number of reasons. We are doing this to see how they get compressed, and how they get compressed has implications on how they transmitted and how they received and stuff. It also has implications of what you can do with it, right? So far we are kind of focused on making the images and video and audio tuned for a human being, not necessarily for processing, right? So if you're doing some other processing with this stuff, some of the things we do may not be acceptable, and that's something that you need to be aware, right? So that's where we kind of are so far. So we spent like about 6 lectures on this stuff, but it's important to understand all this stuff so we can see why we can do what we're going to do next, right? So we start off by looking into compression. And compression is essentially taking this raw data and making it a format that is hopefully smaller. And we'll start off by looking at the lossless, and then move on to lossy, right? And we can allude to this while we're talking about this, but this is more formal, right? So essentially the idea here is you take a process where you give some raw data, and then you get something on the other end, and hopefully the compressed data is smaller than the non-compressed data, right? It need not be true all the time, and we'll see why it need not be true all the time. But in general, that's what you hope. So you take some input data, and then you do this encoding. It becomes smaller, and then you have to worry about how to get the original data back. That's the decompression step, right? And usually you use a metric called compression ratio, which shows the size of the original to the compressed data, and that gives a sense of how good you are doing, right? This goes into information theory really on how the information can be compressed and stuff. And one of the important theories in this field is the Shannon's theory, right? It essentially says how much entropy or how much information is in a particular data, and it's particularly useful for what we're trying to do. And essentially, it quantifies how much bits on average you need to store given the frequency of certain, if you know the certain frequency of the symbols, right? So in a theoretical format, if you think of a particular system which has an n number of symbols, right? So in our case, n symbols would be the integers or the pixels or what have you. So these are n different things that you want to compress. So the data that you're compressing is a combination of these symbols. So if you're talking about 8-bit integers, then you're talking about different combinations of 8-bit integers in a large data. And if you can find the probability that a particular symbol will occur in this stuff, right? So you have a data which is a combination of these alphabets, and if you know the probability of how these things occur, then that equation tells you what is the amount of entropy, which relates to how much information you have to store to represent that, right? It's a very important theory, and it's very useful because it gives you a sense of how far we can go, right? So to give you a sense, suppose you have to, say, encrypt, like, say, this one, right? What this means is you have a system with the strings 1 through 256, or 8-bit amount of value, right? And the y-axis shows the probability that a particular string will occur, right? So that shows that there are 256 different values that are possible in the system, and in a particular object or document or what have you, they're all equal, right? Meaning all the symbols are equally likely to occur. So if you plug this into that equation, it tells you that the entropy of the system is 8, meaning on average you need 8 bits to store that particular data, right? So if you had an object whose probability distribution was like this, meaning it has 256 different symbols, all of them are equally likely to occur, to store them you need 8 bits per, on average you need 8 bits, right? Which means that since the values are from 0 to 256, 0 to 255, 1 to 256, right? You can store them as 8-bit value, right? And there's nothing, you cannot do anything more, because to store this data, you have to have at least 256, each data has to be represented by 8 bits. So compression is meaningless, because the original data itself is 8-bit, and the compressor will be 8-bit. There's nothing you can do, right? On the other hand, if you take this particular graph, right, over here, it shows that there are 255 different values, right? So the symbol space is 255 values, but the probability that a particular symbol, like there are only 2 symbols which have any probabilities. One has a probability of a third, one has a probability of 2/3, right? So even though the possibilities are there can be up to 255 different values, there are only 2 symbols which occur, and the symbols have, one of them is a one of them is 1/3 probability, another is a 2/3 probability. So if you plug the numbers back in, the system can tell you what's the average bit rate. I think the average bit rate for that would be 2. I think it's like, I forget what the number is. It's in your book. It's 1.92 or something, right? So that's the theory. It says like how low you can go, and that's important for you to understand how you build different compression algorithms, right? So the idea here is, if you have something like this, you're good. If you have something like this, there's nothing you can do, right? If multimedia objects tend to be like this, where for a particular, if you get all the values of a particular symbol as equally likely, then you cannot compress them, right? As we will see, we can tweak what we mean by symbols to actually achieve more compression. So even if you have an image where all the colors of the spectrum are present, right, meaning like all the 255 values are present, even if they're equally likely to be present, we may be able to do something using diffing or concatenating symbols to make larger symbols or what have you. But in general, if there's nothing you can do about it, if the probability distribution is equal, then there's not a whole lot you can do, right? The way we use this technique is, if you know these probabilities, knowing the Shannon theorem, we can try to use different representations for those values, right? So intuition here is, if you know that this particular value is occurring 2/3 of the time, and this particular value is occurring 1/3 of the time, rather than using 8-bit for representing these two stuff, I can use a smaller bits to represent this, and smaller one to represent this. So if I do an inverse of the most popular ones, if I give them the least amount of bits, and the least popular one, if I give them the most amount of bits, if I do it right, then I expect to get better compression, right? And that's intuition behind what we're going to see. So we have to somehow find the probability distributions of how these things happen. We find the ones which is most likely to occur, right? Which also occurs most on the data. So we try to assign it smaller number of bits, and we assign more bits to represent less frequent data. And if I do it right, then you get compression. And you can get up to 1 or 2 compression ratios of 1, 2, or 3, so on and so forth with this model, right? And these are lossless, meaning whatever you stored is what you get. But if you compress them and decompress them, you get the same data back, right? And as we sort of alluded to in the GIF model, that need not mean that even for image data you get the same data back, because you may take a 24-bit image, make them into a GIF, which is 8-bit, so you lost information over there. But beyond that, the step is keeps all the data, right? So you may study this also in the theory class as compression, because Huffman coding has strong theoretical background, right? So I'm not sure if this was covered in theory, but if it was covered in theory, their goal is to look at this as a generic data compression algorithm. And here we're trying to see how this applies specifically to media, because media specifically as objects that photographs and stuff like that of naturally occurring phenomena which have certain probability distributions which are different than random images, right? So all the compression we're talking about does not apply for random images like the snow you see when you have your analog TV on some random channels. That data may not compress well with the systems, and that's okay, right? And before we go on to the more details, there are some of the terms that people use. One of them is a memoryless system. Memoryless systems, your future does not depend anything on the past, right? Or the future, the two data is not correlated. Each one is occurring independently, right? Whereas memory-full systems, if you think of them as moving in time, the future sort of depends on the past. Or if you think of them as an image kind of thing, the neighbor depends on the other neighbors, right? So there is some correlation, whereas in a memoryless system, there's no such thing. And the other aspect that I kind of mentioned is the run length encoding, which states that even if you know that there is some sort of a correlation, then you can use run length coding to solve them. So if you assume that some of the data are correlated or some of the data are similar in some sense, I can try to club them and then send, like, instead of sending the same bit over and over again, I can send the count, right? If I expect something to repeat often, then I can send it again, right? So the idea here is if I have, let's say, an input string of AABE, like something like this, right? So in this system, there are two symbols A and B, right? A's frequency is 4 times B, right? So this will probably be, the probability of occurrence of A and B are like this, right? So you may create a system where, let's say, you're storing A using a bit of 0, and you're storing B using, say, a bit of 1, 0, right? So you may transmit them as 0, 0, right? The idea of run length coding is if you sort of expect the data to repeat often, then you could send 0, and then you say somehow mention 0 happens 4 times or so, and that's the notion of a run length coding, right? And again, this only makes sense if you expect this sort of a pattern to happen, and it happens a lot in data, in multimedia data, so we tend to use that, right? So now let's look into how one of the simple lossless compression algorithms. The simpler one is the Shannon algorithm, which is in your textbook. It's not used that much, so I'm not going to go through that in the class. So we'll look at Huffman coding, right? So we take the example of hello, and so let's see. And in this case, we take this hello. Hello has, in the hello in the string, right? L happens twice, so the repetition of L is 2. Every other character is 1, and we want to compress this using Huffman coding. So we specify the Huffman coding algorithm, and the idea here is I have a string which has HELLO. I know the frequency of these is 2, and this is 1. I'm trying to figure out how to encode this such that I get better compression. So I'm trying to find out the one with the most frequent terms. In this case is 2. So I want to assign to the L the smallest number of bits, the other ones larger bits, to see how I can do compression, right? And as you can imagine, in this case, we want to make sure that L is small. We don't particularly care whether H or E or O, how much, I mean, you want them to be progressively larger, right? So this will be the smallest. Since there are 3 other symbols, it may so happen because of the way binary arithmetic works, one of them may have more bits than the other one. But that's okay, because we are looking at a very simple toy example. Once you have a larger data set, that won't happen, right? So the solution we're going to look at may show that L is chosen, let's say 0, and O is chosen like 1, 0 or something. But you can also think of other cases where E has more bits than E, H, or whatever, right? So they're all equal, right? So what we do is, first, we sort them as how these things occur. So we have H, E, L, O, right? This is 2, this is 1, 1, and 1. So we write this as L. So we write them as is a sorted order based on these count values, right? And we internally create tree nodes, right, of the lowest two items, and then replace them back. So the idea here is we take E and O. Ignore this 0 and 1 for now, right? So I'm going to create a new small tree, right? Where this is 1, this is 1. So the count here would be 2, right? So I create the bottom up. I take the lowest 2 values, replace them with this particular structure, and I put them here, right? So I do, this is P1 with a value of 2, right? Then I have to keep this sorted. So this is 2, this is 2, this is 1. Does it make sense, right? So I took the lowest 2 ones, I put them in a degenerate tree. I found it as 2, I inserted them in the right order. Then I look at the lowest, I do this again. I took the lowest 2. So the lowest 2 is P1 and H, right? So let's say I choose a symbol called P2, right? So this will have a count of 3. So if I replace it, it'll be P2, a count of 3, L, a count of 2, right? And then I can create another tree using this. So L, right? And I can label these as 0s and 1s. So essentially, I build a tree with this algorithm. I choose the lowest 2, and I build this tree. And once you build the tree, essentially the symbol for L is 0. The symbol for H is 1, 0. The symbol for E is 1, 1, 0. The symbol for O is 1, 1, 1, right? So what that means is if I finish this and then I have something like hello to transmit, I have to somehow give you that I created this tree, that this is the tree we are operating on. Then I'm going to be transmitting 1, 0, right? 1, 1, 0, 0, 0, 1, 1, 1, right? I would only transmit this bits, right? We're going through all this stuff because since it's variable length now, right? There's not an 8-bit boundary, right? So the receiving end would know what it received because there's nothing which says that this is where the alphabet changes or what have you, right? But if you followed, if the receiving side can decode it because of the way the tree is built, you can decode it back to what you sent, right? So there are a lot of nice properties, right? One of the properties is you will notice that L is the only one which starts with the O, right? So if I receive a O as the first symbol, I know it has to be L, right? So that's the key. The way the alphabets are set up, the decoder would know precisely where it is unless it loses bits. If no bit is lost, he'll know precisely where things are, because if it gets a O, it has to be L and nothing else. If it gets a 1, right, it can either be 0 or 1. If it gets a 0, then it has to be H, right, and so on and so forth, right? And that's the idea behind the Huffman coding. And as you can see, you can have little bit variations, right? There's nothing which says that I should write it as LHEO. I could write it as LOHE or something. It's still the same. What is more, and it doesn't specify that the stuff has to come either to the left or right, right? But you build a tree whichever way is easier for you. So the specific codes may change, but the number of bits that you create would be the same, right? Does that make sense, right? So this is the intuition behind doing this algorithm. And as such, it's not specifically using anything about multimedia. It just uses the fact that this is a compression that is used in Unix compress and all those things, right? So essentially, that's what we're going through here. So after initialization, you kind of set them in some order, right? And so so you generate this P1, replace it into that position, and then you generate P2 and P3, right? And the tree representation is over here, right? So you find the lowest 2, 1, and then create a tree, put them back in the list, sort them again, and then and then repeat till there are no more symbols, and then you kind of figure out what the symbols have to be, right? Does that make sense? And the proof of how these things work would probably be covered in your algorithms course, right? So the nice property is the Unix prefix property, and that's important because we are thinking about transmitting them and all those things. So even if you lose some, so that's one of the important things when you're streaming something, right? This is not related to multimedia, but in general related to streaming, where if you are both talking to each other over a communication medium, then synchronization and is important, right? So if you lose some bits, if you lose some stuff, we would want the other side to get back into synchronization fairly quickly, right? So one way to do that is I can send after each data, I can say, I'm done, or some indication to say I'm done with the particular symbol. We don't want that because those things take up space. So we would like to transmit something where even if you lose track of where you are, you can get back into synchronization faster. So having the unique prefix property helps you because it helps you to start from where you are, right? It still does not help you. So if you lose, like say this bit of data, you still kind of lost, but it helps you get back faster, right? And it's optimal, and the proof of that would be more in an algorithm class. But essentially, it creates a minimum redundancy code, and the symbols which occur more frequently would get fewer bits than the symbols which occur less frequently, right? And again, in this example, we saw that H has fewer bits than E and O, but that's not what it guarantees. It guarantees that L being more popular than any of this other stuff would have fewer bits, right? But the way the binary operates, this happens to have 2 bits, and these happen to have 3 bits, right? But L will always be guaranteed to have fewer bits than the other ones. And since L occurs more frequently, the more frequently it occurs, the more you win because it's occurring more and it uses fewer bits, so you win, right? Yeah.
It says the average code length for the information source S is strictly less than something.
That's the entropy, right? That's the Shannon theorem. The log stuff, right? It has to be less than +1 because the Shannon theorem, it's a real number, right? So you have to round it up to the next integer, right? So the book goes into the extended Huffman code. So the Huffman code depends. So it depends on what the symbols are, right? It's about what the symbols are. In this case of alphabet, it makes sense. In the case of audio, it may be the the particular value that you quantized at any one instant. There may be a bunch of quantization values. So you could treat them all as individual stuff and then compress them. But there's nothing in the system which tells you what the symbols have to be, right? So we as human beings may consider the ASCII code as the symbols that has to be operated on. But it may make more sense to consider symbols to be longer than the 8-bit, right? So the system can be extended to deal with, say, these two as a symbol, because these two are 8-bit values, right? So I can deal with a 16-bit system where the 2 bits are added together to form a 16-bit stuff. So the compression may actually perform better if you extend it. So the extended notion is essentially you take more of these symbols, combine them together to form a larger symbol. And if I talk abstractly in symbols, it doesn't make sense. But if you think of this as I take 2 8-bit numbers, concatenate them to make a 16-bit number, and I apply the same Huffman code, you may get better compression depending on the particular system, right? So that's not a massive improvement. It's in the book if you can follow along. The problem with this system, with the way that I explain the Huffman code, is we need to figure out what these frequencies are. We need to figure out what the frequency of these different letters are, the symbols are, right? So I can do this. So it depends on the frequency for a particular data. So it's not a global thing. So if I want to do this for this particular string, since I have all the symbols, right? Since I have the hello, right? So I know what the symbols are. I know what the popularity of each character is. I'm done with it, right? And it may not be possible to do this all the time, right? So for example, if you're doing a video, if I'm doing a Huffman coding for a video object, I would have to know the popularity of all the integers on this particular video, which means that I have to store all the whole entire video. Then I have to do all the processing. Then I can do the compression, right? Which won't work if I'm doing a streaming video, because if I have to stream, I have to stream it as soon as possible. I don't want to be looking at the statistics, right? So in a practical streaming scenario where I have the data coming in from camera or microphone or something, and my goal is to transmit that to the end user, I would have to find out what these I would like the priorities to be known to me as we move along, rather than doing it all at once, right? So the more practical implementation of Huffman coding would be adaptive Huffman coding, where both of them don't know what the popularity is. We start off with something, and then we kind of learn as we go along, depending on what the strings we see, depending on what the data we see, right? And before we go into the adaptive Huffman, where do you expect the plain Huffman to be acceptable? In terms of the objects that we saw, like audio or video or images, where do you expect the Huffman to be good enough, and where do you expect adaptive Huffman would be needed? Yeah.
Well, if there's normal text, the plain Huffman coding should work.
Yeah, plain text, plain Huffman should work, right? And in terms of the other objects, right, like audio or video or images, where do you think Huffman would be okay? Yeah.
In pictures, if it uses a lot of similar or the same color over and over in the image, you could go by color.
Yeah. So in general, in images, this is useful, right? Images, you tend to take the image all at once, right? You take the image almost instantaneously, the whole scene, and then you're compressing it, right? So it's possible for you to do this analysis, right? Whereas in a video, if I'm taking a video of this room, I don't know if nothing changes throughout my video, then I can take one frame and figure out what the statistics are. Then I can say that'll be the same thing throughout the stuff, right? But if I'm looking at, say, a TV or something, I may see blue oceans for a few minutes, and then I may see red sun or something. So the frequency changes along with time, right? So traditionally, in images, Huffman is good enough. In fact, that's what JPEG does. JPEG uses Huffman because that's all it needs. So in streaming scenarios where you don't know what the future is going to be, you would like to do this adaptive Huffman, right? The reason why you don't do it all the time is it's going to be less efficient than the regular Huffman, right? The regular Huffman knows what the probabilities are. You're trying to learn what the probabilities are as you move along. So for any learning system, for a while, you don't know what the true value ought to be. So you tend to make mistakes. Right? Till you learn the stuff, you tend to make mistakes. But a lot of times you're kind of forced to do that, right? The other problem with this stuff is, if I'm sending it on an image, I can build this tree, right? I can statically build this tree, and then I can send you this tree, right? I can send you this tree to say, the decoder does not have to do anything. You can just have this tree sent to you, and it knows how to manipulate or how to uncompress the image, because it knows the tree. So it can basically say, I saw 1, right? I know 1 cannot be a symbol because of the tree. I know I got 1 0, and I have to look into the stuff and say, okay, 1 0 is H, so I send it out of as H, right? Whereas if I'm doing adaptive stuff where I'm learning as I go along, so if the encoder learns something new, it has to tell it to the decoder, right? So if the encoder finds out that in this case, right, it thinks that the probability of H is 1, E is 1, L is 1, and then it sees L again. So L may create L probability goes to 2. So it may have to change. It may have to rebuild the tree. So it will have to tell the other side that something changed, right? So one way to do that is to keep sending the new tree every time I change something. So the encoder, once it's doing something, it can recreate the tree, send the tree over to the other side, which tends to be inefficient because every time I change something, I have to send the whole tree to you. So now I'm sending this data that is not acceptable. It's not a good thing. So the other approach is to have the decoder also do something, right, and be able to learn what the tree should be based on what the data is coming through, right, and which is what adaptive Huffman does, right. Essentially, the idea here is both the ends start off at the same starting point. Both of them proceed from the same starting point. Both of them build a tree from the same starting point, given the data that is the original data on the encoding side and the uncompressed data on the receiving side. And when the tree changes on the encoding side, the decoding side will see it because its tree will be changed. So they have to use the same algorithm. They have to use the same starting point. And that's a requirement for this kind of system, because otherwise I have to send this tree every time over to you, which is not a good thing, right? Whereas in the Huffman coding systems, I don't have to bother with this, because since I'm going to create this tree once and for all, it's not going to change, I tend to save it with the file. So in a JPEG, I would save the Huffman table with the image, JPEG or any of the schemes which use that stuff. But adaptive, I cannot do that. I need to have the stuff. So if you look at the pseudocode for the algorithm, you get a character, right? On the encoding side, you get a character, you encode it, and then you update the tree, right? On the receiving side, you decode the character and you update the tree. You can send the output, but you update your tree, and this new tree that you're creating would mirror what was created on the sending side. So you don't have to keep sending this data, but they will be sync the way the algorithm works, right? So to begin with, you have to agree on some set of values, right? Some set of values which are acceptable to both, because they have to be the same on both the end. And then as you go along, you change the frequency. So what happens is when the frequency change, the tree would have to change, right? So for example, if E happens to become more and more popular, E may have to move from here to somewhere here, and L may have to move. So when you start off, something may be popular, and they may have smaller number of bits. And then when the tree changes, you may use more bits, and the tree would change. And you always have to make sure that the tree would have the same property. Right? The tree has a property that over here has more frequency than the things on this side of the tree, right? So you have to maintain that, which means that you may have to swap, right? Essentially, what it says is, if this becomes popular, it may have to be swapped with something here, which becomes less popular, and they move around in the tree, right? So to give you an example, so here is a system which has the symbols A, B, C, and D, right? And what you're trying to compress is all A's, right? So since we don't know any frequency about the A's, we assume that all are equally likely to happen, right? So the probability is 1 for the frequency is 1, right? So we create that particular tree over here, right? The A over there, right? It's one possible combination of doing that, but since all of them have a count of 1, you see within the braces, right? So that's one particular tree you can encode. So when you get so from there move on to the B case, right? You receive your first A. So now you receive a second A. So now A has occurred twice. That means the frequency of A has to go up. So you would have to, so in that particular case, A is no longer 1, right? So the algorithm moves it to the end of the current run, right? So the current ones is all ones. So it swaps D to make A here, and then it'll swap those values, right? And again, these are conventions because you want the encoder and the decoder to be the same. You can think of other variations, but they have to be the same on both ends. So after you get the second A, you swap it such that you get the A over there and D over here, right? And so once you do that, you notice that the count at node 6, right, over there now becomes 3, right? The count at the inside interior nodes is basically a sum of both the two. So it becomes 1 plus 2 equals 3, whereas this is 1 plus 1 equals 2, right? So now it's not ordered because the tree has to be thing. So you have to swap this stuff here. So you need to move this over here and move over here because this happens to be 3, this happens to be 2. You need 3 to be here, 2 to be here, right? And once you do that, you actually need one more swap because then this becomes 6, right? This 5 became 6 because now we had the one percolate up. So you need to swap this. So after this, you get that, right? Sorry, this happens only after you receive the second day, sorry, third day, sorry.
So the sender and the receiver are both creating their own trees that are supposed to mirror each other. What happens when data gets lost in between the sender and the receiver and those trees get out of sync?
The system will fail.
Yeah. I mean, do you know of any way that they fix that? Or?
So it depends on the particular system of how we do the error correction. Within the system, you cannot correct the error, right? You have to have other mechanisms to correct that error. Yeah, that's the excellent question. I mean, there's nothing you can do with the system, right? The same way I was saying that, the way it's sent, right? When you look at the first object, you know what, you don't have any confusion, right? So if you receive a 0, it's L, right? But if you lose that 0, then all bets are off, right? Because you don't know where to start, right? But there are other mechanisms you can use to figure out whether there's a loss or something, right? These come naturally with the data, so we tend to use that, right? So essentially, you go through this process. As you get more A's, you tend to do this stuff. So you can see example of how this will operate. Suppose you have a string. So that's the operation, the swap operation, how it works with the previous slide. You can see what happens if you're transmitting a symbol called AADCCD, right? It's interesting because for a little bit, A looks to be the most popular symbol, right? AA is the most popular symbol until the end, in which case D become more popular than A. So for a while, A would be the most popular symbol, right? Even when C becomes equally popular, you can still leave A symbol to whatever it was, right? So in that system, for a while, if you're choosing like 0, I mean, the single digit to be the smallest encoding, A will retain the smallest code value for a while till D becomes more popular, in which case D and A will swap the symbols, right? So while I'm going through the data, the value for D and A would switch over. So in the case of this example we had, A would start off, say, with the symbol of a 0 for a while, but halfway through, when you receive the third D, right? After the third D, A would move somewhere else, but D will become 0, right? So if you look at the data stream, the representation for A would be 0 for a while, and then it'll change over such that D will take over the case, right? And that's what you're trying to do with this, with the whole notion of adaptive compression, and so that's what important, right? So for practical purposes, you use the symbol of a new to show that there's a symbol which doesn't exist. It's a null symbol, right? So when you get the first A, you build this tree with the new symbol, which is essentially nothing, right? And you assign some values to it. So when you see the next A, right, you update the count to what have you. Then when you receive the D, right? So D would make the tree like this, right? It's still you still have the popularity of A to be 2, and D will be here with the new symbol, which is considered to have 0 occurrence because it's not occurrence. It's basically as an implementation aid.
Why do you need to make the tree 2 levels? Why can't you have a 1-level tree with the D on the left and the on the right? Are we trying to keep that new
The new?
symbol? What is the new symbol?
The new symbol is helpful when you transmit this stuff, right?
Is that between each letter?
The new symbol does not actually exist within the system. It's a way when I'm transmitting something, I can say now a new symbol would be transmitted, right? But you can imagine it not being there if it makes the understanding simpler, right? It's an artifact of the way you implement stuff, because we need a way to say when the string ends, right? We can either say it as a fixed length string. So I can say I'm sending you 1,000 characters. So once you decode 1,000 characters, I'm done, right? Or I can use this kind of delimiters to show when things start and when things end, right? So there's an inherent position for new. The new is kind of weird because new is the symbol which does not occur on the input. It always has occurrence frequency of 0 because it never occurs, right? But it just makes the implementation simpler, right? So once you have the C, you go through the same mechanism, right? And when you get 2 C's, right? Now the popularity of C overtakes that of D, so you would have to do a swap, right? The A can still remain where it is because they're both the same. And when you get but once you do that, you have to do a swap over there, right? Because the C would mean that the root would now have 2 + 1, 3. So 2 and 3 you compare. So you have to swap it so that A goes here and C goes here, right? Then once you have the next D, it's okay to be here. But when you receive the next D, then things have to change because now the D has to be I mean, we're not going through the steps over here, but essentially D would mean that D cannot be here, right? D would have to move up and it has to move over here, and A would have to be swapped here, right? What this means is at this point, D's encoding is 0 and A's is 1, 0, 1, right? And before the last D was received, A is 0 and D is 1, 0, 1, right? So then the value for D goes from 1, 0, 1 to 0, and A goes from 0 to 1, 0, 1. And if the other side is building the same tree, then this will be natural, right? Again, if you lose synchronization and if you lose something here, then it's undefined, right? So the way you transmit them is if you look at the symbol, the code is what you transmit, right? And the new is useful as a way to say what happens. So the first A you transmit, you transmit it as 0001 because that's the generic one. You have no frequency, right? And then once you get these characters, you figure out what the symbols are, right? Going back to the previous slide. So at this point, D happens to be 101. So if you have to transmit any other stuff, A would be 101 and D would be 101 after the step because D was transmitted thrice, right? And the key here is that it changes along the way, and both of them have to run the same algorithm, but they have to be in the same state. So they will do that, right? So we'll see how they actually do that. Actually, it's in the book. I didn't go through that stuff, right? So essentially, if you both keep track of the stuff, you would know the stuff. So the receiving side, if it's building the same tree, it will know when this thing changes, right? So this is not going to be as efficient as the Huffman coding because while you're learning this stuff, so if you're done the real Huffman coding, you would have noticed that D is the most popular one. So you'd have sent D as 0 rather than this 101, 101 for a little bit. But like I said, for streaming scenarios, you're kind of forced to use adaptive scheme, right? There are other popular lossless compression algorithms, and the other popular is the LZW, which is what is used by GIF. LZW is a dictionary-based scheme, right? So essentially, if you have a dictionary, if you have some sort of a dictionary, it builds somehow, right? So you can choose words and replace them with numbers. So if you find a word and to be very popular, so whenever you see the word A and D, you can replace that with something. So I need to send you the dictionary and the symbols I use. So I can say dictionary for A and D is 1, and so on. So I can compress it based on the dictionary. So I'm still using the same, each symbol is the same size. But now I use the fact that the combination of the symbols are a certain way, right? So each of this, so if this is 8-bit, this is 8-bit, this is 8-bit, this can also be 8-bit. But I'm having a combination of these symbols to represent one of them. So if I send you the dictionary and the encoded one, then you can uncompress them by doing a lookup on the table, right? So that's the notion of LZW. And the more longer sequences I find, the better I win, right? So if the dictionary is lean, right? If all I can find is only one character is unique kind of stuff, then I don't win. But if I see longer and longer sequences, I win, right? So if for example, if I have, if I expect a character like this to happen often, I can then count it as 1 or something. Then the longer the sequence I can find, the better compression I can get, right? And again, it depends on how you build the dictionary and how you use the stuff. And it's again a popular algorithm. And it depends on what you expect on the input stream, right? The more repetition you have, the more you can replace them with one string, and that's how it works, right? So the Huffman coding is one form. Dictionary-based coding is another form. All of them are lossless. So all of them, you have to build this data structures. But once you build the data structure, it's lossless because whatever you send, you will uncompress to the same value, right? So here's an example of how the LZW actually works, right? So we have the string called ABA, BBA, BCA, BAB, BBA, right? We want to build this dictionary, right? So we have to figure out what combinations of words occur most frequently and hopefully replace them with a smaller set of sequence. So one way to implement that is, without knowing a priori what the different input symbols are, is this the algorithm that we describe here. And when the algorithm goes through, it only transmits 1, 2, 4, 5, 2, 3, 4, 6, 1. So instead of sending 14 characters, it sends 9 characters and 9 codes, right? So bitwise, it's not gaining anything, but it sends fewer characters because it finds repetitions which are replaced with something else, right? So you get a compression ratio of 1, right? So I'll try to go through this algorithm. So essentially what happens is you look at the current character and the previous character, and you build this algorithm to figure out what the output should be, right? So let's start off by, we don't know anything about the input. So let's start off by assigning a code of 1 to A, 2 to B, and 3 to C, right? That's the base case because we don't know anything about. So first we see the character A, right? The first we see the character A, we have to go to the next character. So when we're seeing the current character is B, the previous character is A, right? We look to see what we know about B and A. There's nothing we know about those two symbols. So we have to output the value for A because I don't know anything about, there's no pattern so far with including A and B, right? So I output the code for A, right? and then I mark a code for, then internally create a code for A to represent the strings A and B, because I just saw A and B. I don't know what to do with them, but I output the value for A. I remember this, right? So next time, my previous character would be B, a new character would be A. I've never seen this pattern either. I've never seen B and A. So I output the character for B, which is what I should have seen. So I output that. Then I remember that I saw this pattern, so I remember BA. So next time I get the symbol B. So previous was A, current was B. I've seen this pattern before, because if I look over here, I think I've seen this before. So I don't do anything. I don't output anything. So next time, the previous ones that haven't been sent out is AB, and the current one that is coming in is B. I never seen this pattern ABB before. So, but I know I've seen AB, which happens to be the code 4. So I output the code 4. Internally, I remember that ABB would have been a code 6, right? Again, this is a case where I'm building this thing on the encoding and the decoding separately. So I don't have to keep transmitting this stuff. So I would have to output 1, 2, 4, 5, and if you go through the algorithm, essentially you look at here, and at some point we reuse this ABB, right? ABB will be built here. We see this pattern again, so we transmit that. So, yeah.
What are the S and the C that the pattern versus the
So S is the previous character, and C is the current character. So in the first A, you don't do anything. So you have to go to the second character. So when you see the second B, you kind of see what your current character is and what your previous character is to figure out what the dictionary should be, right? The key here is, this is string matching algorithms. Again, you'll see them a lot more in your algorithm class. You're trying to figure out what are the strings, the longest possible matching string, right? Without looking too much into the future, right? So you're looking only at the past to figure out only one bit in the past to see what the patterns are. If it looks like so in this case, you see A and a B, but you've seen this A and B before. So you hold that, and then you get the next symbol. So next iteration, you see whether you've seen ABB before. You have seen ABB, so you win, right? But you've never seen ABBA before. So you learned this here. If the stream was to continue on, the fact that you saw ABBA would help you in the future because it gets you stuff, right? So the longer the algorithm runs, the better you get compression, because you tend to build this dictionary more, right? And I'll repeat this in the next class because we're sort of out of time. But there is a limit to how far you can go. You can't build this dictionary infinitely. So practical reasons, you may have to purchase a dictionary after a while. But when you start off, you don't get much compression because you haven't seen anything. But as you move forward, if you have patterns in the input stream, you tend to catch that and you get better compression, right? Again, these are lossless. These are generic compressions, but they're useful in the multimedia case, right? And we'll continue on Friday.